Welcome back, folks. This lesson we're going to take care of part 2 of 5.2, analyzing functions with the second derivative. Okay, in part 1 we looked at how the second derivative dealt with the concavity and inflection points of functions. What we're going to do with part 2 is get into a couple of applications of concavity, including the second derivative test, and then some other stuff with local linearity. Here we go with that. Let's go ahead and get into the criteria for the second derivative test. And it's going to be a test just like with the first derivative test to find minimums and maximums of a function. Okay, how the second derivative test goes is if f prime of a equals 0. Okay, so in this case, let's say this is where our a is at, where our function takes on a local minimum. Okay, f prime of a, the derivative of f equals 0, is going to happen when we have a horizontal tangent. Right, so we've already looked at that for finding critical values. Now, as far as how do we know if that is a minimum or a maximum, we're going to look at our second derivative. So if f prime of a equals 0 and f double prime of a is greater than 0, we know we have a relative minimum because we know that when f prime is greater than 0, our function's concave up. So if we have a critical value on a concave up interval of the graph, we know that's got to be a bottoming out point, that's got to be a minimum. Okay, same idea for finding local maximums. If f prime of b equals 0, let's say that this is our b value, okay, where this function's derivative is 0. Okay, so we have that horizontal tangent line, a critical point. And f double prime of b is less than 0, which will happen when our function is concave down, then we know that f has a relative maximum at x equals b. Okay, so that's our second derivative test. Find our critical values just like with the first derivative test, and then instead of looking at sign changes of the first derivative, we'll just look at what the sign is of the second derivative. Alright, so let's look at some examples of applying the second derivative test. Problem 2 part A says let f of x equal some polynomial. We want to identify the x values of any extrema of x. So in other words, find the mins and maxes. Okay, 2 steps for that. Step 1, we'll find the critical points. And those are going to be the points where the derivative is either equal to 0 or does not exist. So let's find the first derivative of our f. F prime of x will be equal to a 3x squared minus 12. And that's it for this one. Pretty straightforward. Let's figure out where that derivative is equal to 0. So that's going to be when our 3x squared minus 12 equals 0. Okay, solving this guy, we can add 12 to both sides. Alright, we can divide both sides by 3. And we can take a square root on both sides of the equation. So we'll say that x is equal to plus or minus 2. Okay, plus or minus because we took the square root. Alright, so those are the critical points, the points where we could potentially have a minimum and maximum. Again, we'll use that second derivative test to determine, okay, if they are in fact mins and maxes. Alright, so getting into the second derivative test then. What we're going to do is we're going to look at the second derivative of our function. So f double prime of x is just our derivative of the first derivative. That's going to be just a 6x. All right, and then to figure out whether we have a minimum or a maximum or neither, what we'll do is we'll plug our critical point values into that second derivative. So again, instead of looking for sign changes of the first derivative, we'll just plug them straight into the second derivative. So we'll look at f double prime of negative 2, which is equal to 6 times negative 2, which is equal to a negative 12. All right, so our second derivative is negative 12. In other words, our function is concave down at x equals -2. So looking like this. Okay, so what kind of point are we looking at then? Well, if we have a critical point on the part of a function that's concave down, that means we're looking at a maximum. So we can say, so local max at x equals -2. All right, so there's our second derivative test in action. Again, instead of checking for sign changes of that first derivative, we're just checking out the sign of the second. Let's do the same thing for our other critical point, f double prime of 2. And that's just equal to 6 times a 2, which is equal to a 12. And I guess just like with some other tests we've had, the only thing we're really worried about is if this is positive or negative. It's positive. Okay, so we know that when our second derivative is positive, our function is going to be concave up. So opening up like that, and if I have a critical point on a function that's concave up, that'll be a minimum. So we have a local min at x equals +2. And just like with our first derivative test, not a bad idea to graph this function here. Okay, what I'm seeing when I pull up the graph, it goes off the screen a little bit, but I can see that at x equals -2, I do in fact have that maximum value, and that's going to be happening because my function is concave down. If there's a critical point when it's concave down, it'll be a max. And same idea, there'll be a min down below here at x equals 2, where my function has a critical value of 2 and is concave down. We can tell that's a minimum. All right, let's take a look at a few additional examples. Polynomials are nice to kind of get things going, get some nice pictures, but let's look at some uglier stuff here. Same idea, let g of x equals 2x squared minus ln x for x greater than 0. We want to find the extrema, okay, using that second derivative test. So first step, find the critical points. For that, we're going to use our first derivative. Okay, derivative of 2x squared is going to be a 4x. Minus derivative of natural log is just 1 over x. All right, then we want to figure out where that derivative is equal to 0. We did one like this in a previous lesson. Let's say that 4x minus 1 over x equals 0. Okay, solving, we can add the 1 over x to both sides to get a 4x equals 1 over x. And to get rid of the fraction, what we can do is multiply both sides of this guy by x. That'll cancel my fraction on the right and leave me with a 4x squared equals just a 1. Then we can divide both sides by 4 and end up with x squared is equal to 1/4. And take a square root on both sides of the equation, which is going to leave us with x is equal to, plus or minus once again, square root of 1/4. Okay, square root of 4 is 2, so that'd just be a 1/2 for this one here. All right, now notice with this one, there's an additional kind of stipulation on this function. It's only for when x is greater than 0. Okay, reason for that is if I think in terms of my logarithmic function, my natural log function, if I graph that, I know I'd have an intercept at 1, 0. The graph would look something like this. Let's actually hit that point with a vertical asymptote at 0. Okay, so in other words, it's never equal to 0. It never crosses over into negative values. So this function's undefined below 0. Derivative will be as well. That's why as far as critical values, we can lose the plus or minus. It's just going to be the positive 1/2. And then other thing with this one, we would want to consider where our function's derivative is not existent, okay, where it's undefined. Okay, notice I do have division by an x here, so 0 wouldn't work. But once again, we're only looking at above 0. We'll take a look at kind of the issues with denominator in the next example here. Okay, so find my critical points. And for this one, that's just a 1/2. Now, we want to determine if that is a minimum, a maximum, or neither. And that's going to be the second derivative part. Or second derivative test, in other words. Let's go ahead and find that second derivative. Now, I suppose with this one, we've got our first derivative kind of written like this, which is nice for plugging values in. But it might not be a bad idea to rewrite that as 4x minus x to the negative 1 power, kind of getting it ready to go to actually find the derivative. All right, so g double prime of x then will be equal to derivative of 4x is just a 4, minus derivative of x to the negative 1 will be multiplied by the negative 1, so plus x to the negative 2 power. In other words, our g double prime of x is equal to 4 plus 1 over x squared. Okay, equivalent expressions, but the bottom one will be a little bit nicer for substituting critical values in. Okay, so there's our second derivative. We just want to figure out if our function is concave up or down or neither at this critical value. So we'll look at g double prime of 1/2. That's going to be equal to 4 plus 1 over 1/2 squared. Okay, which we could actually quit at this point because all we're really worried about is whether it's positive or negative. I can tell this is going to be a negative answer here. But I suppose we could calculate it. 4 plus 1 over 1/2 squared, 1 over 1/4 in other words. Okay, flip the reciprocal, that'd just be a 4 plus a 4, or an 8 in other words. All right, so my second derivative is positive. That means my function at 1/2 is concave up. So what is this critical value going to be? It's got to be a minimum. So we have a local min at x equals that 1/2 value. And then once again, probably not a bad idea to pull out the calculator after the fact. Okay, take a look at what we're looking at. Does it make sense? And I'd say, yep, we're seeing we have that critical value at 2. It is in fact a minimum because my graph takes on the shape of concave up. And then like we saw here, our function isn't defined for x. It's only for x greater than 0. There's nothing on this side of the graph. Okay, because again, our natural log is undefined for anything less than 0. Let's take a look at the second derivative test one more time, just applying it to a different type of function, rational function in this case. Now, you already know how to find the first and second derivative of this h of x. Okay, we've already showed you how to apply the second derivative test, so I'd recommend pause the video, try working through this on your own here. I'm going to run through in a second, but it's good to practice and try these. It's better than just watching me do them. All right, so here we go. Apply the second derivative test. We want our critical point, so we need our first derivative. Okay, here we're talking about a rational function, so we're thinking in terms of the quotient rule. D over dx of a function divided by another function was the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over denominator squared. Okay, so that's what we're dealing with here. So, fraction, denominator on top, times derivative of my numerator, derivative of x squared plus 4, just be a 2x, minus the numerator, that x squared plus 4, times derivative of my denominator, which is just a 1, okay, all over x squared. Okay, let's clean that up. H prime of x, we could say is equal to, here we'll have a 2x squared minus x squared minus 4 all over x squared which we can simplify down to just an x squared minus 4 all over x squared. Okay, so there's my first derivative. And we want to figure out where my first derivative is both equal to 0 and then also we want to look at where my first derivative does not exist for critical points. Okay, it'll be equal to 0 where the numerator is equal to 0. Okay, zeros of a rational function are just the zeros of the numerator. So setting x squared minus 4 equals 0, we end up with x squared equal to 4, and that's going to be x is equal to plus or minus 2 once again. And as far as where that derivative does not exist, that's where my function's undefined. Okay, that's going to be the zeros of my denominator, so when x squared equals 0, that happens when x equals 0. Okay, which makes sense because it looks like we're going to have an issue with that original function as well. I can't have x equals 0 for that part. Okay, so I've got my critical values, and this is a good example where I'd say the second derivative test kind of works a little bit nicer. It's going to be easier to plug values into that second derivative than check all the different signs and intervals, okay, that we get with our first derivative test. So we'll get this out of the way here. I should have made my eraser bigger. There we go. All right, so next up, let's find the second derivative. H double prime of x will be equal to, okay, going down to this guy here, denominator normal, so x squared, times derivative of my numerator, just the 2x once again, okay, minus my numerator, x squared minus 4, we're subtracting the whole thing, times derivative of my denominator, 2x once again, all over x to the 4th. Okay, we can clean that up as we'd have a 2x to the 3rd. And distributing here, this would be minus a 2x to the 3rd. And then minus a negative 4 times 2x would be plus 8x. All over that x to the 4th. All right, and this one cleans up pretty nicely. My 2x to the 3rd and minus 2x to the 3rd will cancel. And that leaves me with just an 8x on top. Well, one of those x's will go away as well. So we can reduce this down all the way to h double prime of x is equal to an 8 over x to the 3rd. All right, so there's my second derivative. Now what I want to do is plug my critical points into that. And again, this will be, I'd say, definitely simpler plugging things in here as opposed to checking signs, okay, for intervals with this guy. So we'll look at h double prime of negative 2. That's just going to be equal to 8 over a negative 2 to the 3rd. Okay, again, I don't actually need the value. I just need to know if it's positive or negative. That will be negative because raising to the 3rd power keeps it negative. That'd be an 8 over 8. 2 to the 3rd is 8. Negative 1, in other words. Okay, my second derivative is negative, meaning that my function at negative 2 is concave down. So we could say local max at x equals negative 2. And then we can do the same thing with h double prime of positive 2, which would be an 8 over 2 to the 3rd, which is just a 8 over 8, which is a 1. Okay, second derivative is positive, meaning that function is concave up at that point, meaning we have a local min at x equals 2. All right, and I suppose that last critical point then, we do have the 0. Again, thinking back to our original function, it's undefined at 0, so I'd expect the second derivative test to not give us anything. If we look at h double prime of 0, well, that's just 8 over 0 to the third, which is undefined. Okay, if we click back to the way we defined the second derivative test, we only said it applies when our second derivative is greater than 0 or less than 0. Doesn't tell us what to do when it's undefined or even equal to 0. Okay, so in those cases, if you couldn't tell what you had, you would have to kind of do something else, possibly the first derivative test, to come up with a conclusion on those points. And then once again, like normal, we'll pull up the graph. Okay, take a look at what we're looking at. Yep, I see my maximum at x equals -2, minimum at x equals +2. Again, it's a good practice to graph these after the fact here. And the last thing we'll talk about dealing with the second derivative, just one additional application of it is going to deal with local linearity or using linear approximations. If we want to use a tangent line to approximate the value of a function f of x at a given value of x, so let's say we have some function here, and the function maybe is difficult to work with. Let's say it's going to be easier to write the equation of a tangent line to that function at a point to make approximations, okay, such as if we want to know what f of this point is here, we could look at this point on the tangent line. Okay, we can make an approximation, but I'm going to say that the approximation will be an overestimate if our graph is concave down on the interval that contains x. Because as we can see here, anywhere that our function is concave down, our tangent line is going to be above it. Okay, so if I have any points on this tangent line, they'll be above the graph, overestimations. And then the approximation will be an underestimate if f is concave up on the interval containing x, because wherever my function is concave up here, that tangent line is going to be below the actual function. All right, so let's go ahead and apply that idea. It's really just combining concavity with the writing equations of tangent lines we've been doing all semester here. So problem 3, let's say for a twice differentiable function f of x, it's known that f of 2 equals 7, f prime of 2 equals -3, and f double prime of 2 equals -3 as well. We want to use a tangent line approximation at x equals 2 to estimate f of 2.1. Okay, so that's nothing new there. And then we'll also answer, will this be an overestimation or underestimation? We'll take a look at that in a second here. Okay, so tangent lines, we're just writing linear equations. We can fill in y minus y1 is equal to m times x minus x1. Okay, our point slope form of equation. Now for the x, we're looking at x equals 2. And we know the y at x equals 2 because we have f of 2 equals 7. So we can just say that y minus 7 is equal to, we'll fill in the m in a second, parenthesis x minus 2. And then my slope, the slope of that tangent line, is by definition the value of the derivative of x equals 2. So for that, we'll use this -3 here. All right, so there is my tangent line. Probably going to be nicer to plug things into the point slope form. So let's go ahead and solve that for y. Y minus 7 is equal to a -3x plus a 6. And then add the 7, add the 7. That's going to give us y is equal to -3x plus 13. Okay, so that's going to be a line that's tangent to the graph at x equals 2. And what we can use that for is to make approximations of our f at values close to 2. Okay, maybe this is a function that isn't very nice to plug values into, or maybe it's not an equation of a function at all. Maybe we just have some points in the form of a table or a picture of it or something like that. So we can find f of 2.1 and say that's approximately, so squiggly line equal to, negative 3 times 2.1 plus a 13. Okay, so in other words, negative 6.3 plus 13, that'd be a 6.7. Okay, so f of 2.1 is about 6.7. Now, second part of this question, we want to know, will this observation be an underestimation or overestimation? Well, for that, what we'll look at is our second derivative. It is negative, meaning that our function is concave down where we made this approximation. When the function's concave down, the tangent lines are going to be above them. Okay, so if we can think of this as, again, we don't know what this function looks like, but if this is 2, we looked at 2.1. Okay, again, since we're concave down, that is going to be above that graph, which is why this is an overestimation. All right, part B is the same idea. Why don't you take a minute, pause the video, work 3 part B, and then press play to check your answer out. All right, that's it for lesson 5.2. Why don't you go ahead and give the homework a shot, finish up the homework, I should say, and like usual, make sure you're getting help if you need it.